Hello, I'm Jiwen fan. I'm going to talk about my DOE early career project, which is about understanding physical factors impacting past and future severe convective storms in the central United States. I would like to acknowledge many of my collaborators, particularly my postdocs as listed here. Severe convective storms are those produce hail, tornado, strong winds, flash floods. Robust predictor of the severe convective storms and the associated hazard is not possible yet because in the current climate model, because of coarse resolutions, and also because of a poor understanding of the physical factors impacting them. In the past decades, the environmental factors such as global temperature, the warming, and the land use land cover change, and the anthropogenic aerosols was significantly changed and will continue changing in the next few decades. So the science questions we are trying to address is that what are the significant interactions of the storm dynamics with those physical factors of global warming and urbanization, which changes land use land cover change and aerosol, as well as wildfire, which also changes those parameters. And then we want to look at what are the joint and respective effects of these factors on the severe convective storms in the present day and the future climate. And so we have this two-step approach. In the step one, we are improving our fundamental understanding of how the storm dynamics would interaction with these physical processes to improve our understanding. And we have done quite a bit of study on this, which I will highlight in the next few slides. And currently we're focused on the step 2, which is about going further using the convective permitted scale model to look at the long-term statistical effect. And this way we'll do this. For example, we'll select 4 warm seasons for the present day and future climate. So here I will talk about the urbanization effect. We did the 2 studies for 2 different types of the storm. One is the supercell storms influenced by Kansas City, which produce hail, tornado, and strong winds from the Pecan Field campaign. The other one is the sea breeze-induced thunderstorms over Houston. The common finding from the 2 studies is that the joint effect of the urban land and the anthropogenic aerosols is larger than either of the individual effect. And basically, without consider both, we cannot simulate the observed convective intensity, precipitation, and the hail and the other features. And then another point is about relative importance of the urban land effect versus the anthropogenic effect. They are completely different between the 2 different storms. So this highlight resolving the storms is very important to accurately simulate those effects. So for the Kansas storm, we found that urban land, so we have this is replaced the urban land with the cropland, and then the urban land, with the urban land we have a stronger storm as the initialization, and then the storm was pulled toward the Kansas City. It's become much stronger and also pass over the Kansas City. However, without the open end, the stone is much weaker and also move to the northeast of the Kansas City. Then for the hailstones, we actually find there's a strong nonlinear amplification effect when they work together. The individual effect, this is for land effect, this is for aerosol effect, both of them are not large. However, when they work together, we find a much stronger effect. And overall, the land effect is much larger than the aerosol effect. However, for the Histones sandstones, we find a very different story. The aerosol effect is dominant for the precipitation rate and also the convection intensity. This is probably also because of the very low aerosol background, the background aerosol with the Houston region, while our Kansas City, the background aerosol is much higher. We do find that our Houston, the land effect changes the sea breeze, enhances the sea breeze circulation, which enhances the stone development from the warm phase to mixed phase clouds. So as you can see here, anthropogenic effect on the hailstones. In this study, we selected the typical hailstones of the central United States, which are generally from two major synoptic scale patterns. One is the front system. This associates a strong mid-troposphere trough. They have characteristics of cold temperature, low cap, and strong wind shear. The other synoptic pattern is the Great Plains low-level jet. They are associated with a strong North Atlantic subtropical high, and they usually have warm temperature and higher cap compared to the front systems. They have similar productivity of hail, however, their response to global warming is very different. For the front system, we have up to 60% increase in the severe hail, but for the low-level jet systems, we didn't see much sensitivity. This is not because of the response of the meteorological conditions to the warming is different. Instead, it's because of the cloud dynamics response to the warming is different. So in the front system, the convective intensity is enhanced in the future climate. This leads to much enhanced group and hair formation, mainly through more supercooled droplets. However, in the low-level jet systems, the convective intensity is already much strong. It's stronger than the front system, and it does not increase further by increased cap anymore. Then we don't see much sensitivity in the hair. Another effect is because the warm cloud layer depth is larger in those systems, and they are also have a larger increase in response to the warming. So that's contributed to also the smaller effect. So here the significance is that by linking with the synoptic scale patterns, we can improve the understanding of the predictability of the hailstones in the future. Here is a wildfire impact. What we did is that first we build this model capability in Wolfgang to account for heat fluxes impact, and this is usually not considered in the model. So without consider both heat and aerosol effect, we will not be able to simulate the hail, the large hail, and the loss of latency. So the aerosol effect in the later stage after the stone is triggered by the heat plays a very significant role. Here is about the non-statistical analysis about the factor contributed to this very large hail interannual variability over the Great Plains. So we also did 2 studies and for SGP and NGP respectively. What's interesting here is that we found the factors impact the large interannual variability of the hails is very different between the 2 regions. So over SGP, the aerosol loading from the northern Mexico plays a very significant role. And then the sea surface temperature anomaly over the northern Gulf of Mexico, then is the answer by controlling jet streams. Then for NGP, the major impact is from the advection of water vapor from the warm region due to this associated with the North Atlantic subtropical high. Then the answer is just additional common factor. So we have all the major studies that are supported by this project, which I don't have time to highlight. If you're interested, I'm happy to talk with you on those things. One of them will be presented in the breakout of the extremes. The next work, well, as I mentioned earlier, we are focused on this long-term statistical studies about how those factors, the warming, urbanization, wildfire would impact the severe storm characteristics of the central United States. We also will employ the machine learning approach to understanding the processes and factors affecting the predictability of those severe convective storms. We'll have a long-term goal where actually through the regional refinement at 3 kilometer resolution and the global cloud resolution, when E3SM is ready, we will use those and also machine learning methods to gain robust predictive understanding of these severe convective storms. Thank you.